Hello, everybody. Thank you for coming. Thank you for choosing this track with my talk. So today, I'm going to try to explain how can you implement a search index using one of my two favorite technologies, Go and machine learning. I'm going to be floating around maybe in the way of the things, but probably it's okay. So my name is David Hernandez. You can follow me on Twitter if you want. If you don't want, it's okay. I'm not going to chase you. What I do for a living is I work in this little project that is called Machinebox. It's machine learning as a service. So we deploy machine learning models in Docker containers that everybody could use in their own premises. And it's pretty good. You should check it out. And we are part of this bigger company that is called Alberene, that you can also check it out. What are they doing? But today, we're going to talk about search. How many of you implement search in their own work? A lot of people. It's very common feature that you have to implement. Like every single feature, every single product that you work has some kind of search. So we are used to use these search engines like Google, DuckDuckGo. By the way, use DuckDuckGo, it's pretty cool. Stack Overflow, have you used Stack Overflow? Yeah. Amazon to buy some things, is just a few of them. So why search is important? Because the main thing is increase revenue. So the main example is if you find the product that you are looking for very, very quick, you generate more revenue. So I'm a fan of Nintendo Switch, so that's the first example that I thought. But also, it could reduce the cost. So if you find the information that you're looking for quickly, for example, how to add the build version in a Go binary, if you type that in a Stack Overflow and the first answer is what you're looking for, it can save you a lot of costs, like looking for other things. Also in customer support or things like that, finding the right answer is pretty good. And the third one is makes users more happy, because it's like the I'm feeling lucky thing, isn't it? If you just click it and you have what you're looking for, it's just, oh yeah, I'm happy. So you probably don't have to implement search by yourself from scratch. So you rely on some kind of software to perform search. My two favorites are Elasticsearch, obviously, very widely used. This one is not widely used, but I like it a lot. It's Redis Search. It's a module on top of Redis, so you can use to implement full text search on Redis. And the thing about these engines is they are based in an old formula, an old statistical formula implemented by humans that is called TF-IDF, term frequency by inverse document frequency. What does, it's a very complicated formula, but it's basically a way to match keywords. I'm going to prove that very shortly, that is only matching keywords. So I think Slack implement search with Elasticsearch, and if I have a good keyword to search, like GopherCon UK, I search on Slack, two nice gophers like Dominic and Kat, they have a good answer because they mentioned that keyword in the search. So it's pretty good search. I was looking for that, so pretty good search. But what happened when I ask a question? So if I ask a question, does Go have generics? The first answer that I get in a Stack Overflow is a JavaScript answer. That's not really good, isn't it? It really doesn't understand what I mean. What it does is try to match the keywords. So basically highlight the keywords that it found. But that keyword doesn't mean anything. It's just a good matching, but it doesn't retrieve the information that I'm looking for. Okay, so can we do it better? Can we apply some new techniques or other techniques to make our search understand what we are saying? Yes. In the last years, the machine learning is been developing there are a lot of investment in machine learning, and we can use NLP, natural languages processing, to try to make our search better. So, for example, I ask Google these days, how long do dogs live? And it really understands the questions. It just tells me, oh, from 10 to 13 years. That's pretty cool. It really understands what I'm saying, what I'm trying to look for, and it gives me an answer. And that's probably using some kind of machine learning behind. Also, not really search directly, but when I write an email these days, I use a lot auto-response by Google, like quick auto-response. That's kind of a search, isn't it? I'm trying to, my query should be my email, and I'm trying to find from all the answers what is best to me. Anybody using this? Sometimes it's a little bit scary, isn't it? It's too perfect. It's like, oh, I don't write so perfect. Yeah, I just commit some mistakes. Okay, so let's try to use machine learning, do some science, and trying to implement search using machine learning. So that sounds really complicated. Like, oh, how can I start? So I'm going to try to make it in just 2 simple steps. It's going to be marked with this symbol, so we all know in which step we are. So the first step is, in machine learning, we tend to use numbers. More concrete, vectors. It's just an array of numbers, basically a array or a slice of floats. Sometimes we call it tensors for some reason. I don't really know the reason, but yeah. So the whole idea comes to this. So we have some text, and we wanted to transform it to vectors. So any kind of text could be a document, could be a paragraph, could be a sentence, or even a single word. We can try to transform it in vectors. How are we going to do that? So there is a popular implementation in machine learning that is called War2 Vectors. It seems very complicated, but as I said, in machine learning only understands numbers. So when we have a categorical variable that is, for example, words or text, you cannot directly represent that into numbers. So for example, if we want to represent the days of the week, we transform that in what is called one-hot encoding. And that's as simple as we have an enumeration of the days of the week from 0 to 6, like it should be, not for 1. For every single day of the week, we set a number to 1, if it's the day of the week we are, and the rest to 0. In that way, we can encode the day of the week with just a slice of 7 numbers, isn't it? And that's pretty cool. That gives a representation of my little words that are the day of the week in a vector. But that has a problem. It doesn't reflect what a day of the week is. Even for a machine, it really doesn't matter if it's Monday or Saturday. But as humans, we know that Monday is very different from Saturday. So what about if instead of representing the days of the week in one-hot encoding, we do it with a 2-dimensional vector. So instead of a flat structure, we can plot the days of the week in 2 dimensions. So with that, we can put Monday, Tuesday, Wednesday together, Thursday and Friday around here, and Saturday and Sunday around there. So we can easily, in 2-dimensional space, draw a circle in the weekend, or group the first days of the week, or clearly see what is the middle of the week, isn't it? It's just much better representation of days of the week. So it captures the meaning of a day of the week. So the good thing is we don't have to do that ourselves. There are machine learning algorithms that they calculate this representations in vectors for you. And that is exactly what happened with War2 Vector representation. So you feed a lot of text to this algorithm. It's completely unsupervised. The first versions are unsupervised, and it calculates good representation for words. Good representation means if you do simple mathematical operations like sum, rest, divide, and so on and so forth, you can get nice transformations, anagrams, and things like that. For example, you can have a mathematical operation that transform Spain to his capital, like Madrid, and so on so forth. You can apply the same mathematical operation, and you can just get transformations. So it's a good representation of words in the space. And that's pretty cool. So if we want to implement that in Go, these models comes in a form of CSV. So for every single word, you have the vector representation of the word. So the only thing that we have to do is load that CSV and put it in a map of a stream float. So you can have an index of all your words in a simple map. You can also log the dimension of the vectors and other things to be able to use it. So if we want to get the vector representation of just a single word, we only need to pass to look for that word on the index. If it's there, I return the vector representation. If it's not there, I consider that word out of the vocabulary that my model understands, and just returns all zeros, and it should be fine. Cool. So, but hold a second. We just made the conversions between just one word to a vector, but my text is not just one word. It's usually a sentence, a paragraph, or a document. So how can I put together, for example, a sentence and transform it to a vector? So the good thing about these vector representations, they are pretty good with mathematical operations. So if we want to represent the quick brown fox, famous phrase for some reason, we only need to sum all the numbers and calculate the average by the number of words. And surprisingly, this works very well, very decent well. Yeah. I was surprised at the first time that I found out about that. So if we want to vectorize a sentence, the only thing that we need to do is, given a sentence, we need to tokenize the sentence, just split by white space in many languages. For each word or each token, we vectorize the token, like with the War2 Vector representation. So we vectorize that word. We accumulate that word to calculate the average, and at the end, we just return the average. So we can just represent a sentence in a vector space. And that's also pretty cool. Cool. We are nearly there. So just remember, in the first step, we try to transform every single text to a vector. So in the second step, so imagine that we have everything transformed to a vector. So we want to search be able to perform search in that vector. So what we can do is have this interface that, given a query vector, some limit of results, it returns some results that is just also a key value pairs with the business value, the business key, and the vector, and the distance of that vector. So we can rank how close our data is to our query. Okay. So that sounds really complicated, but at the end, it's a problem that is solved long time ago. So it's when you want to perform that, it's the nearest neighbor search. Usually, you don't have to implement that yourself. unless you are in an interview. So if you use the right data structure to represent your data, like KD3 or BP3, the search performs really in a really good time, and the insertions are mostly OK. So you can use one of these data structures to perform the search. So I have this little library that is BP3. It's based in another project, so you can check the original source. But there are other libs in other languages or as a service that you can use to put all your vectors in it and perform search. The most famous one probably is the Spotify ANOI. It's widely used. But yeah, pure Go implementation is the BP3 that it works well. So how I use a BP3? So the API is very simple. You just has an item has a key that is usually the business key. It could be anything, and the vector. So you put everything into the tree, and you just perform the search. The distance of your query vector to that target vector is your ranking. So far, so good. So as quickly as that, I explained step 1 and step 2. We just quickly see what it was. So step 1 is just convert all your text to a vector and put it into a BP3. So now I want to search. So I convert my query also to a vector, and I perform the nearest neighbor search given your query vector and all my data. And that's my results. Yeah, as simple as that. It wasn't too difficult, isn't it? Cool. But is that really working? It's just as simple as that. So I made a little user interface to prove that this could be a good approach. So I download a BBC News dataset. It's just BBC News with different categories like tech, business, sports. It's a public available dataset, but remember that this is from 2002, 2004, so it's not very recent. OK, so let me show you the little demo. So it's kind of very standard kind of user interface. Is made for showing the results. So the first thing, I'm going to try to search for stock price falling. So on this column, I have the results from Elasticsearch. It highlights the keywords. So it says, oh, stock price, stock. Yeah, it makes its job, but it's not really getting the meaning of the sentence, isn't it? It's a stock price falling. I want to see some better results. So if I show my War2 Vectors search, the first results say, oh, it not only highlights just the keywords, it highlights the sentence that it thinks that is most important. So in this sentence, it really says, oh, the stock price is going down, or the market is going down. Even if it doesn't mention, well, it mentions stocks here, but it doesn't mention the word falling or something like that. So it really gets more the meaning of what it's saying. Yeah, it has more results. So I play around with that for a bit. And this third implementation, I'm going to explain what it is a meaning, but it's another kind of model that converts sentence to vectors. And also it's pretty good results. Markets fall on weak dollar fear. So it's kind of similar results. So what does it mean? So Elasticsearch is really good for matching keywords. Nadal. So it's a search for Rafael Nadal, that is a tennis player. Probably, yeah, Rafael Nadal is a good example. So I have a good keyword. So Elasticsearch is pretty good matching keywords. So I got these results first. And it's pretty good because is the results that I'm looking for. In the downside, the other models, they don't do the hard matching keywords. They're just trying to understand the meaning. So if War2 Vector knows more or less that it's about tennis, but it doesn't find a hard match of Rafael Nadal. And the universal sentence encoder, the first results that it found is about Federer. Oh, yeah, it understands about tennis, but no, it's not Rafa Nadal. I want to search for Rafa Nadal. So in that sense, Elasticsearch is pretty good matching keywords. So let's go for something more controversial. Yeah. So remember, this is a 2002-2004 data set. So in 2002-2004, nobody knew about Brexit, isn't it? So because it's matching keywords, Elasticsearch doesn't find any results. Makes sense. Probably nobody in the news mentioned Brexit. War2 Vectors is a pre-trained model. I download that from the internet. So it's probably a little bit older, so it really doesn't know much about Brexit. But Universal Sentence Encoder seems to know about Brexit. So even if this is an old data set, for example, it retrieves these results that is talking about EU referendum. That's pretty good, isn't it, for information retrieval and discovery? That's quite amazing result. So it kind of works. Let's go back to the presentation. So one of the problems with War2 Vectors, and we saw in the examples, is that it's biased to the pre-trained data. So I use a pre-trained model. So it has little context about the problem that I'm using to solve. And most important, out of vocabulary words are not represented. In that example, War2 Vectors didn't know about Brexit. So how can we do it better than just a pre-trained War2 Vector? So the solution is I can train my own War2 Vector model. Probably the easiest way is use this library. So I can pass all my tests in my problem and calculate and generate a CSV with all the words and the vectors adapted to my problem. And that's probably going to generate much better results for your search. So it's something that you can quickly do. It works pretty well. But what about if we go further? So in this example, we are trying to go to just get one word and transform it to a vector. But we can do more like end-to-end solution. We don't have to get into just one word. If we have enough data and enough examples, we can go further and try to transform directly, take one sentence and transform it to a vector. And that's what the Universal Sentence Encoder by Google does. It's a TensorFlow model that you give it a sentence, and it produces a vector representation of that sentence. If you train your own model, you can apply it to anything. You can give a whole document and try to get a vector representation of that document. And it's a really powerful concept. To use that model, it's a little bit more fancy than just processing CSV. It's just calling TensorFlow in Go that is a little bit verbose. So you have to open a session, set the inputs and the outputs, but at the end, we're just gonna get the vector representation of that sentence. I'll return it back to my search, and all supposed to work like it was working before with the previous War2 Vector model. So yeah, that's pretty cool. Okay, so I'm almost at the end. So what are the takeaways of this presentation, in case you are sleeping? Machine learning can really help you to extract not only keywords from your query or your documents, it could try to find what's the meaning of that sentence. Also, I don't know if you ever try to adjust the relevance in Elasticsearch or other other search solution. But it's pretty difficult. You just end up adjusting too many things and optimizing for one use case. Using machine learning, you can just control the input and the output very, very well. So you can, I think you have better control of your relevance. And the most important thing, you can impress your users. You can have that I'm feeling lucky experience. You can make your search look smarter. I don't think solutions like Elasticsearch, they're gonna go away, but they're probably gonna incorporate a solution like War2 Vector, or try to plug a machine learning model into Elasticsearch or other search solutions to make some search better. I think that's all I got. Thank you very much.